Okay, so I hope the screen is visible.
Yes, ma'am.
Yes, ma'am.
Okay, good. So let me just do a quick recap of what we did in the last week. So we started looking at search problems, and we sort of looked at these components where a search problem contains a state space, a set of actions, and a successor function, which, at each state for an action you take, where do you land up? And what is the cost? That's what the successor function gives you. And you also have a start state at which the whole process begins, and there is a goal state. Okay, so the idea is to start from the start state and get to the goal state, and you want a sequence of actions which take you there. So you can think of this as these problems in navigation. And yeah, so the sequence of actions which take you from the start to the goal, that's what is called a plan. Okay, and we saw an examples in Pac-Man where, for eat all the food example, you model the location of the Pac-Man and the food positions and the positions of the capsules and so on. Okay, and so these are some things you write down for each problem, the actions. So in this case, it was north. The which way do you go at each location, whether you go north, east, south, or west. And we had the successor function, which typically becomes very large because you define it for each state. Okay, and for each state action pair. Okay, so these are some of the things we did. And another example was finding a route from IIT to the Chapura fort. And we defined all these quantities. Okay, so this is what we did, and we told what a plan corresponds to in this example, and the objective is to find some plan. Okay? You should be able to reach the goal. And in this regard, we also looked at some other representations. So one was called the state space graph, where the successor function, to be more precise, that gets modeled using this graph. Okay, so you are at a start state, you take some actions, you get to some other states. So this graph depicts the entire successor function. Okay? And from this, you can read off the plans. So this is one way to represent your problem. And other representation is a search tree. So where you explicitly enumerate this whole, it's like an expansion of the state space graph, right? So it's also a graph, but it's a tree. So you start from a start state, you take all the possible actions, where do you land up? From there, what are the possible actions? Where can you land up? So the idea is kind of similar to the state space graph, but the only difference is that there can be repetitions in the search tree. So here, the repetitions are taken care of by each state just appears once in the state space graph. Okay, you take care of these repetitions by the direction of the arcs accordingly, but in the search tree you explicitly list them out. So it's kind of a listing of all the possible plans. Okay, so every branch of this tree, if you enumerate, you're going to get a plan. Okay, and what you're going to do is you're trying to find a plan from the search tree or the state space graph. So because of the compact representation, we usually prefer a state space graph. The search tree is going to be useful. Today you will see some things like how do you do an analysis. So there the search tree concept is very useful. Okay, and so we also saw that the state space can become really large and it can be exponential. So typically what you do is you don't store the entire state space graph in memory. What you do is as and when you require, you generate the this graph. I mean, you generate parts of this graph as and when you need it. Like you generate this, you write a function to generate this at a state. If you have this action, where do you land up? The successor function itself, you generate it as you go on, rather than storing this entire graph in memory. Okay, and yeah, so that was what we did. And we also saw one algorithm to find a plan. So this was the depth first search algorithm. So it's almost identical to what you learned in your algorithms class, the depth first search algorithm. The only difference is that you now care about the sequence of actions. So the one that you would have seen in algorithms would be to do a traversal of all the states. So here you're going to do a traversal with the objective of finding a goal, finding the goal state, and also you care about the particular actions, the the labelings of the edges. That is an important quantity for AI. Okay, so but otherwise the algorithm is quite similar in the sense that the implementation makes use of a stack, so which you all know is a last in first out structure. And yeah, we also saw the algorithm. So the idea was to go depth wise. Okay, you expand the graph depth wise. Okay, and yeah, so we also wrote out the algorithm. So this is where we stopped last time. So are there any questions so far? Is it clear so far? I need to hear some answers. Yes, no, or any questions? It's clear? Okay.
Yes, ma'am.
Okay, cool. Okay, so now we saw the algorithm, and let's just try to do some analysis of the depth first search algorithm. So, we had these things that you first push the start state, and you kind of do this repetitively till the stack is not empty. As long as the stack is not empty, you keep popping states. And so one thing is you also push the path so far, because we are interested in the actions, in the sequence of actions. You also push, what is the path that you have traced till this point. When you yeah, when you push, and I mean, so here also you should have an NT maybe. Okay, so because you, or maybe an S because you are pushing the current state, or yeah, maybe just an empty, because I think what you need is a sequence of action, so just an empty. And when you pop out, you're popping out the state and the path so far. Okay, and then what you do is you're pushing all the neighbors, if they are not visited. Okay, and so this kind of goes on till you find the goal state, right? And so let's just see. So you can also think of it in terms of the search tree. Okay, so what happens in the search tree is you have the start state in the root. Okay, and then you have like different possible sequence of, I mean, different possible actions you can take from this, from the start. And again, at each level you have maybe some more actions, and you get different states and so on, right? So like this it will go on, and you'll have the tree goes on up to some depth. Okay, so let's say that the depth is, say, some, so let the depth of the search tree be D. Okay, so this is a search tree, and suppose its depth is D. So we also saw that the search tree can become infinitely large, right? It can go on and on if there are cycles. But in terms of the DFS algorithms, you're taking care of this aspect by seeing that if this part of the graph, so suppose this node, so let me put it with some color. So suppose this node is going to get repeated in this part of the graph. Okay, so all these nodes essentially come down. So maybe not here, somewhere here. Okay, let me say, so that it's easier to understand it. So suppose this is the same node that comes here, and so this entire tree is going to get repeated in another part of the graph. Okay, so but you're handling this because once you find that this state is visited, you're not going to do anything more. It's as if this for this branch, the second branch here which repeats, it's as if this gets cut off here. Okay, because you're not going to explore anything after this once you know that this was already visited earlier. Okay, so for all practical purposes for analysis, we'll assume that there is a depth of D. Okay, there's a finite depth of D. um, okay, so I hope this distinction is clear. Okay, so now what DFS amounts to is you start from the start state, and maybe you take the leftmost node, you visit this state, and you go further ahead, and so on. Okay, so when what you do is you will push all these entries into the stack. Now you will pop this, maybe the first one out. I mean, or whatever you last pushed in, you pop that one out, and now you push all its children. Okay, and then what you do is you again pop one out, and this process go on till you finally reach a leaf node. Okay, so if this is the goal state, then you're done. Otherwise, what it does is it goes back and again it explores this node. So this is the child of some other node here. So like that, it will proceed. So in some sense, what BFS is doing is it's giving you the it's exploring this plan first, the leftmost in some sense. In very loose terms, it's exploring the leftmost plan. If you don't find a goal state, then you go to the next leftmost plan and so on. So you will then explore this one and so on, right? So this is the kind of trajectory DFS is going to follow. Okay, so there are some things that we care of, some metrics. So one thing is it complete? So completeness of the algorithm. So that means that are you guaranteed that you will reach a goal? So are you guaranteed to reach a goal? Okay, so this is what it means to say whether an algorithm is complete. So what do you think? Is DFS guaranteed to give you a goal state?
Yes, ma'am.
Yes. So why is that?
For ma'am, it will go through each and every node at some time.
Yeah. Yeah. Right. So, every node of your state space graph or your search tree will get visited, and it could end up, covering the entire tree. So, if your goal is somewhere here, you might end up visiting the entire tree. But the point is, you will surely cover every node of the tree. So, yes, it's complete. Now, another thing we care of is it optimal in the sense, does it give the smallest sequence of actions?
No, ma'am.
So, it doesn't give. Why do you say that?
Ma'am,
Ma'am,
because
yeah, it's brute forcing through all the nodes.
It's brute forcing through all the nodes. Yeah, it's actually not fully a brute force, right? There is a structure to it. But yeah, the idea is right. So, Advait, you also wanted to say something?
yes, ma'am. So basically, it's just returning the first possible plan that we find. But in the tree, there can be some other path which we have not yet discovered, which can be smaller than the currently found path.
Yes, exactly. So that's exactly the idea. So the thing is, the search tree is going to be something like this. Okay, so there can be a goal here, and maybe there was a goal here. Okay, uh, but what this is going to do is, it might find this one first because it has, chosen this one to explore first, and it's gone, very much into the tree. So then, it will not give you this goal, right? So in that sense, yes, it's not optimal. Now another thing we care of is the time and space complexities. So let's just analyze this. So have you done some time complexity analysis in your algorithms class earlier?
Yes, ma'am.
Yes. Okay. So here also we will do the time complexity and analysis. So what we want to essentially find out is how many nodes do you end up visiting, or how many nodes in the graph, or how many, if you look at it in terms of the search tree, how many nodes are really explored. Okay. Finally, it's going to give you one plan with a set of actions. That is okay. But in the process, how many nodes do you end up visiting? Okay, so here, what is the worst case? I mean, when does DFS take the maximum amount of time? Can you tell me?
Ma'am, we have to visit all nodes in worst case.
Yes, in
Yeah,
the
when
worst case.
the node is rightmost.
when the node is the rightmost, right? So if the goal is somewhere here, this is where it's the worst, right? You'll have to end up covering the entire search tree. So in that case, how many nodes would you explore? Suppose you don't have anything like repetitions in the entire search tree. Okay, so then in that case, how many nodes would you explore? So let me give you some more numbers here. So let us say that just for convenience, let's take that every node has b children. Okay, so every node has b branches. Okay, so that's where b. Every node, has b children. Okay, so in this case, and the depth of the tree is what did we say? It was d, right? What? So depth is d. Yeah. So the depth of the tree is d. So then in that case, how many nodes would we explore? Okay, so the goal is in the rightmost. So goal is in the rightmost. So this is a very loose term. Okay, so the rightmost in the tree. So how many nodes would be there? So in the start state, so let's say that this is level 0. Okay, so this is let's just say depth itself. So depth is 0, and these nodes are all in depth 1. Okay, and so on up to finally you have a depth of d. The entire depth of the tree is d. Okay, so in this at depth 0, how many nodes do you have?
B to the power D.
Okay, so at any depth you have b to the power d nodes. So at depth 0 you have one node, at depth 1 you have b nodes, again at depth 2 what you're going to have is b square nodes, and so on, right? So I hope that computation is clear to you all, right? So if you have any questions on this, just stop me. Okay, so b square and so on, and finally you have a depth of b power d. So the time complexity is just going to be, the sum of all these nodes, because you end up visiting each of these nodes. So it's just going to be b power 0 plus b power 1 plus so on up to b power d. So order of this. So you'll also have some operations to manage, but overall the number of operations is this much. And so what would this be? So this is a geometric series, right? So what does this evaluate to? Guys? Okay, am I audible?
B power
B raised to the power D plus 1
plus 1
minus 1.
minus 1 upon b minus 1.
Yes, b power d plus 1 minus 1 by b minus 1,
Yes.
right? So this is order of this, and this is roughly order of b power d. Okay, so I hope you all remember. Do you all remember the order notations that you learned?
Yes.
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 Yes. Okay. So yeah. So that's why this is order of b power d. Okay. So in that sense, it's not nice. The time complexity is not very good in the worst case because it can be exponential. Okay. So now let's also look at the space complexity. So the space complexity here is with reference to the stack. So at any time, at any point of time, how many entries can be there in the stack? Okay, so that's what we will refer to for the space complexity. So how many entries in stack? So by entries, I'm just going to think of it as, one structure with one state. Okay. So I'm not thinking of, the path so far and all that. It's only with respect to states. I'm just going to count the number of states. How many entries in stack? Okay. So to see this, to analyze this, remember this structure, right? Like you first push the first start state, and then its children, all its children you push in. So this part that you haven't read is going to be there. Now you are going to pop one of them, and then you're going to put, so here there are B entries, and from the next state, again, you're going to push, in the next depth, again, you're going to push B entries. And you will remove this one, maybe one of them. And you again push some more B entries in the next level, and so on till finally you're at the at the leaf node. Okay, so here again you will push in B entries. So all these entries will be in your stack at some time. All these states will be part of your stack. So how many entries would that be?
Ma'am, it can be like B minus 1 into D.
B minus 1 into D, right? So, right. So we'll just say it's order of B times D. So it's actually B minus 1 into D in the worst case, but that minus 1 is for the root, right? I mean, for the level 0, right? Sorry, it was B minus 1, right? Not B. B times D minus 1. Is this what you said? Right. Who answered?
Ma'am, Raghavendra.
Raghavendra. Okay. Okay, so this is the thing, right? B times D minus 1, right? And yeah, so in order notations, like in asymptotic sense, it's just order of B times D.
Ma'am, I think
Yes?
it should be B times D and minus 1, just a single subtraction.
Okay, yeah, that's true. So BD minus 1. This is what you're saying,
Yes, ma'am.
right?
Ma'am, but every level we remove one node, no? Like if we
Yeah,
traverse level.
yes. Every level you will remove one node. So
So ma'am, so how can it be like B into D minus 1 or BD minus 1?
yeah. So no. So what we are saying here is just in terms of the order notation. So it will not exceed this, right? This is an upper bound, and at max one more node. So maybe you will have in each depth maybe one more D, right? So BD minus D plus 1 you might have, right? But in terms of the factor which matters, it's this product it's order of B times D. Okay. I hope this is clear to you all,
Yes, ma'am.
right?
Yes, ma'am.
Yes. Okay. So I want to also hear from others also. Tanuja, is it
Yes,
clear?
ma'am. Yes, ma'am.
It's clear. Maybe let me ask some more people. Um, Ashutosh, is it fine? Does it make
Yes,
sense?
ma'am.
Yes. Okay. So, were there some questions in the chat? Okay, you answered here. Okay, I didn't see this. Sorry. So, please stop me, okay, in case there are some people asking questions in the chat because I don't see it. So anyway, so coming back to DFS, so these are some of the things, right? It's complete. You will be guaranteed to find a goal. It's not necessary. It's not necessarily optimal, and the time complexity is going to be order of B power D. And in terms of space, you will have order of B times D. So this is not too bad. B times D is a good. It's a reasonable amount to have in the stack. So this exponential is when things get tend to slow down. Okay, so now you've seen DFS. So naturally, the next algorithm is going to be what?
BFS, I guess.
BFS.
BFS, exactly. Okay, so let's do that. So the next one is Bfs Search. Okay, so here the idea is rather than going deep into the graph, you expand the nodes like in a flat manner in some sense. Okay, and what is the data structure you use for Bfs Search?
Ma'am,
Q.
Q.
Queue. And what is a queue?
Ma'am, first in, first out. FIF.
Yeah, first in, first out structure. So if you're going to have a list like this, if you start, so the number, suppose you have something like this. This is the order in which you, inserted the elements into the list. Okay, so this came first. This was the first entry. This was the second, and so on. And so now, if you are going to, remove elements from this list, this is the first one which will be removed. Okay. Whereas if it was a stack, the last element is going to come out first. So this is exactly like if you are in some counter and there's a queue, right? So the name comes from there. So whoever has stood first is going to get served first. Okay, so that's the thing. So here, what you will do is it's the same algorithm, but instead of pushing items onto a stack, you're just going to push items onto a queue. Okay, so again, let me just maybe do some example, like a very small one, maybe is. Okay, so A, and maybe like something like this. Let's take this graph. So I want to also put something which comes back here. So maybe let me put this edge also. Okay, so here what you will do is you will start pushing, start inserting items into the queue. So the operations are called NQ and DQ. Right, so NQ is an insert and DQ is remove from the queue. Okay, and so first your queue is going to have S, and in terms of the sequence of actions, it's just empty. And now you're going to dequeue from the queue. The queue is, the queue is having some elements, so you will dequeue. So now in the next step, so this is the first iteration. The second iteration, what's going to happen is you're going to, all its neighbors, you're going to insert into the queue. Okay, so this is A. Okay, and yeah, so when you pushed S in, you would have marked S as visited. So let me just put a tick here. So S has been visited, and what you do is now you push in, so you NQ, so I shouldn't say push, so you NQ C and A. So let me NQ in this order, A, state A, and the sequence is I'll just write this as SA. Okay, so actually it should be the label for this app, whatever action took you from S to A. Okay, so here it was just S, or maybe let me just label it so that it's a bit clearer. Okay, so I'll just call it A1, A2, maybe A1, A3, A2. So these are the actions which took you. So initially there was no set of actions. Now you went to state A via the action A2. Okay, so your queue is going to have this entry first, and the next entry is going to be this C, right? So you're going to have C, and you're going to have A1. Okay. Now, what you're going to do is you're going to remove elements from this queue. Okay, so the first element that was pushed in was A, that comes out. Okay, so next what you're going to have is this is going to be visited, right? And yeah, then what you have is you're going to you're going to NQ its children. So what you're going to have is CA1. So this is already there in the queue, and you're going to NQG. So this is the goal state. Okay, and you're going to have actions A1, A2 and A1. So A2 is what you had so far, and you're going to have this additional action A1. Okay, so maybe this is like a too quick example because you ended up already finding it, right? Okay. Yeah, so maybe I should take a slightly larger example. Okay, so let's just do. So maybe I'll just choose another example. Okay, this is too small. So let's just do the same example that I gave you as a homework. So I'll just write it here, C, B, A, and yeah, you have something like this, and you have an F, go from S to F. Now you go to D, to D, to D, and E and G. Okay, so let's just do some runs of BFS here. So what's going to happen is you will initially start with S, it's an empty. So this is the first step. Now you will remove this from the queue, and so you also need some actions, right? So okay, I'll just call it like this: A1, A2, A3, A4, A5, A6, A7, A8, A9, and A10. Okay, and so if the first entry was S and it was an empty list, and now you know removed this from the queue and you marked this as visited, and what you're going to have is now C A1. Okay, so this is going to be the first entry, and then you're going to have F A2. Okay, so this is another entry of the queue. Okay, now what you're going to do is you're removing something from here. So the first entry gets removed and you'll mark it as visited. Okay, and so what are its children? So you have B, and this is not a child because it has an inward arrow. You have B and D. So right now what is in the queue is F with A2. Okay, this is going to be your first entry. Now you're going to insert in the end of this queue. So you're going to have B, right? So B is going to be there, and you're going to have A1 was this path so far, and you're going to append A7. So this one, right? A7. Okay, so A1, A7. So this is the next entry. Okay, and what is the other child? You have D, right? So D is going to come in with A1, A3. Okay, right? So yeah, so this is the next set of entries. And now when you do a DQ operation, what's going to come out is F. Okay, so this is going to get visited now, and you're going to mark F's children, right? You're going to mark F's, you're going to push in F or NQF. So here you're going to have D, just D, right? So I guess, so this is fine. So D, A1, A7. So this is already there in the queue. Next, you're going to have D, A1, A3, right? And you're also going to have D, A2, A4, right? So D with what did you push out was F, what did you remove was F, and you had this action list was just having A2, and you're going to append A4 to it. So A2, A4 comes in. Okay. Right. So this process goes on. So if you see the way we marked things as visited, you started off with S. Now both its children are ending up getting visited, and now in the next step, what is going to get removed is B. So C's children, right? So B is going to get removed, and then also so in that order. So B is coming out, and next D also. So D from here. So this is also going to get visited. So it's in that order, right? So basically, if you think in terms of the search tree, what you're going to have is a root node, and then you're going to have all its children. Okay, so all these are going to get visited, okay, before the next level gets visited. Okay, so you will visit this, then all these will end up getting processed, these will get visited, and in the next step you will end up visiting all these. Okay, and further this whole level, in fact. Okay, all these are going to get level visited. So it's in some sense it's like depth wise you're going to visit all the nodes till you finally hit the goal node. Okay, so in terms of the algorithm, it's going to be the same as what you did in DFS, but instead of a stack, you're going to use the queue operations. So it's the same thing. So you will start off with an empty set, and you will first insert the start state. And when it's not empty, you will remove the state and the path so far. and you will mark it as visited, and then you will push all the, or you'll enqueue all the neighbors. Okay, so the algorithm is exactly same as this, just that instead of stack you use a queue. Okay, so any questions on the algorithm itself or the way it worked? Is it clear?
Yes, ma'am.
Yes.
Yes, ma'am.
Okay.
Yes,
Yes.
ma'am, it's clear.
Okay.
Yes.
Okay. Okay. Cool. So yeah, this is about it. So now let's. I think you guys already know the BFS algorithm, so I'm just kind of quickly going over it. So let's just do the same analysis like we did for DFS. So is it going to be complete? So are you guaranteed to find a goal state?
Yes, ma'am.
Yes, ma'am.
Yes. So same logic, right? Like everything is going to get visited. You're not going to leave any part of the tree out, okay? Because you're going systematically throughout the entire tree. Now, is it going to be optimal? Is it going to give you the smallest sequence of actions?
Yes, ma'am.
Yes.
No. No, ma'am. I think because in the previous example we have visited D node twice.
Uh, if the weights assigned to all the actions is same, then it will be the optimal solution. Uh, Otherwise, we may or may not get an optimal solution.
But ma'am, in our state graph, weight for every state is one, na?
Yes, there is no, no. I mean, all the actions are the same. So there is the cost is the same for all the actions. Okay. Okay, so let me address these points. So what all of you said is right, like Gunjan, Raghavendra, what you guys pointed out is right. So if the costs are all equal, it's going to give you 1. Okay. Tanuja, your question was about D being visited twice.
Yeah.
Yeah. So what is going to happen is, you might end up visiting some, state twice, but what we care of is only the goal state, right? The goal state is going to be visited only once, because the moment you identify that, there is a goal here, you're going to stop. Okay. So in terms of the algorithm, so maybe let me just copy this and, make the required change. So, so the only difference is here you're going to have a queue. So let me just write it as queue. So this is the difference. So you're going to have a queue, and these operations are in the enqueue. So queue.enqueue. Okay, and again, while this is queue, and wherever you have L, it's actually you replace it with a queue. So what happens is, see Tanuja, like when you see the goal state, so as you're pushing in or enqueuing items into the queue, the moment you find a goal state, you're just going to return the path. So that is this step. Okay. So you're not going to visit the goal state twice, right? In terms of, okay, so what's going to happen is you're going to visit B. So as per our algorithm, the next thing was to visit B. And then what you're going to push in is A. So let me just do it once, so that it's clear. Okay, so, sorry. So I'll just skip the actions, okay? So B, D, D. So now B is coming out, and what you're going to have is A. So these are the 3 states, okay? But here for this D, the sequence of actions is A1, A3. For here, it's A2, A4. And for A, it's now you have A1, A7, A8. Okay, so what's going to happen next is B was done. So now you're going to come to D. So you will mark it as visited. Okay, so that is from this step, A1, A3. Okay, and then you will mark, you'll enqueue D's children. So what is now there in the stack is A2, A4. So D with A2, A4. Then you have A with A1, A7, A8. And the next one is E. Okay, and with the action, what did I write here? I can't read my own handwriting. A4, A5, this is A6, I guess. Okay, so this was neighbor of this D. So A1, A3, A6. Okay, so I'm sorry, it's just gone. Okay, so now D has been marked visited. Okay, so now the next in the queue, when you see there is again another D. So now what is going to happen is you've already marked it as visited. So this is going to come out, but you're not going to again push in an E. You're not going to insert E because D was already handled. Okay, so all its children have already been in the stack. So you just, for this path, you just stop it here. Okay, so this D was A to A4, right? Like from this path. So that just culminates there, and you will just proceed with A1, A3, A5, like that. Okay.
Okay,
So,
ma'am. So
okay.
we just, if it is already listed, we just dequeue it without adding its children.
Yes,
Okay,
exactly.
got it. Thank you, ma'am.
Okay. Yeah. So remember, all these further processing happens only if it is not visited. Yeah. So this is a good point. It's worth spending some time to analyze it. Yeah. So in that sense, so when we look at optimality, so Tanuja, one point that you raised is about states being visited multiple times and such things. But in terms of optimality here, what we are talking of is only about the sequence of actions. Okay, is it the smallest possible sequence of actions? You can define many other things like how many times do you end up pushing things into the stack? Is it optimal with respect to that? So that is a different analysis in itself. Okay, so yeah, there are different notions in which you can define optimality. Here we are looking at just the sequence of actions. Is it the smallest possible sequence that you get? Okay, and for this, yes, it is true that you are going to get the smallest sequence of actions, because if you think of the algorithm, what are you doing? So you are visiting nodes in the order of the depth, right? So everything which is in this depth 1, will get visited before depth 2. Depth 2 will get visited before depth 3, and so on. So even if you have a goal here and a goal here, okay, so what it's going to do is it's going to visit this last goal, this one, even before it visits this goal. Okay, so in that sense, that's the reason why BFS is going to be optimal. So you see, these kind of things get very clear. The analysis becomes extremely clear when you think in terms of the search tree rather than the state space graph. But the algorithm to write it, to think in terms of what is visited, and so those things, it's easier to do with the state space graph. Okay, so that's about optimality. Now, the other thing is, yeah, the complexities, the time and space complexities. So let me write it here itself. So, what is the time complexity of BFS? So, any thoughts? What's the time
Ma'am, B to
complexity?
the power D, I guess.
Right. Because of the same reasoning, right? You might end up, if the goal state is here, then you will end up covering every node of the tree. You will end up expanding every node of the tree. So that's why this is also going to be order of B power D. Okay, it's just the same calculation. You sum up all the nodes of the tree. Okay, now what about the space complexity? So how many entries will be there in a queue at any point of time?
Ma'am, I guess the time complexity should be same as space complexity should be same as time complexity, B to the power D.
B to the power D.
Yeah.
Okay, so can you explain why that would be the case?
Yeah, ma'am. In the worst case, like if we at last level, i.e. at depth D, then for each
Mm-hmm.
node there will be its child, like there will be B to the power D childs, and they will all be in queue.
Yes, exactly. So that's the reasoning. So at any point of time in the queue, you will have the entire level, right? So see the queue that we had, right? So we had S, then we had C and F. So these are all the level one nodes, the depth one nodes. Okay, and at the next stage, what we had was all its children, right? So if you draw the states, the search tree here. So what did we have? So there was C, there was F. Now for C there is B, and what else? BD, right? And as far as F is concerned, you have a D. So that's it, just the D. And now for B, there is an A. And for A, again, there's a C and so on. So for D, now again, there's an A and there is an E, like that. Okay, so I'm just not writing the whole search tree. But if you see the stack, what's going to happen? First, there was just this one node. Then you had C and F. So what you had was actually this whole level, this whole depth. And after you removed F, what you had was B, D, D. Okay, you had this. Okay, and if once you would have finished D, you would have had the next level, and this process would go on and on. Okay, so at any time you are you would have like B power D. If you are in the stage where you are visiting nodes at a depth D, you're going to have B power D nodes in the queue. So if the goal is in the last level, what you're going to have is, and suppose it was somewhere here, the goal was here, this entire set of nodes will be there in the queue. So that's why the space complexity is order of B power D. Okay, so I hope this is clear to you all. Any questions?
No, ma'am, it's clear.
Okay, so fine. So do you have a class after this? I wanted to show you a demo of BFS and DFS in action, but if you have a class and need to wind up, I can do it tomorrow.
Yes, ma'am, we have a class after this.
Okay, fine. So let it be. So we will, maybe I will just show you the demo in the next class. So we will stop here for now. And, if there are any questions, I'll hand back. If not, thanks everyone.